So K model equation in K omega model, of course, because the last term in the K epsilon, in the K model equation, the K epsilon, it has an epsilon, minus epsilon, that we cannot solve it here. So I need a modified K equation, right? So that is straightforward. We get essentially dou K by dou T plus uj bar dou K by dou xj equal to dou by dou xj of nu plus nu T by sigma K dou K by dou xj, and then the pk term, no change in the production rate of K, because that is Reynolds stresses followed by mean strain, no change occurs here. Pk is appears to be the same there. Now minus of epsilon was there, instead now it has to be epsilon by beta star K, that is what we used it. So this becomes essentially beta star K omega here. So your sync term becomes minus beta star K omega, which is the only new term in the K equation, so slightly modified. So this is your equation 3. So equation 2 and 3 together will have the K omega model with the eddy viscosity, the ratio of K by omega. Okay, so this is what I have. And yes, so the model constants that we have to look at. So the model constants, we have beta star, it's essentially C mu, they call it beta star here, but they give the value as 9 by 100. So if you see in literature, this is the value declared, but this is actually C mu in my opinion. This is nothing but 0.09, but you will see this 9 by 100 in the literature. And you will also have this sigma K omega in the where is it, here, this particular one they call it sigma K for the omega equation, of course. So the sigma K omega equal to sigma omega, both is taken as 2 model constant here, and the C omega 1 and C omega 2 is what I am telling you because it is consistent with C epsilon 1, C epsilon 2. In literature they use a different terminology for this. So what they are using is essentially alpha or gamma, this is what they use, but I am simply using this as C omega 1. This value is 5 by 9. Okay, and then I have C omega 2. This is again they use beta or C omega 2. The value is 3 by 40. So these are the model constants that are required to complete the entire K omega model here. Now we have to look at the behavior. Okay, the model is fine, but is it giving numerically stable or not? So let's go back and look at this equation 2 and 3 to see whether this is numerically stable or not. Okay, so now consider this, consider K omega model behavior. That is your equation 2, 3, and then okay, I can call this 4, then make this 3, then the 2, 3, 4 completes the whole equations here. So that is equations 2, 3, 4 near the wall. So if we take the eddy viscosity, that is the straightforward part, nu T as y tends to 0, K tends to 0, that we know. So this will not create any problem for you because it's k by omega. It was not creating any problem elsewhere also. K square by epsilon was also okay. So this is goes to 0. So it is stable, no problem here. Similar to the k epsilon. We look at the k equation. This is equation 4 here. K model equation. So again, same arguments, gradient terms on the left hand side and the diffusion terms. Okay, so the gradient terms will not create any issue. Gradient terms are fine here. The first three ones, that is not a problem. We only look at the pk and the beta star part. Pk is same as before. There is no change in the pk, right? So pk is nothing but your 2 nu t Sij over bar minus 2/3 k delta ij dou ui bar by dou xj. Only the value of nu t is k by omega. So that is also not a problem. Nu t goes to 0, y goes to 0, pk also goes to 0. Not a problem, right? So this is nu t is nothing but k by omega here. So this is also okay. So this is production rate goes to 0, stable. Okay. So then the last term beta star k omega is not a problem because k goes to 0. That is also fine, right? So you have the sinc term, which is sinc term beta star k omega. So y goes to 0, k goes to 0, stable. No issue here. So then we look at the omega equation, okay, which is equation 2 here. So I can look at this particular part. Let me just copy this. Okay, so this is my epsilon, or sorry, the omega model equation, right? This is the omega model equation. Again, gradient terms will not cause any numerical instabilities. Gradient terms are fine. Here c omega 1 pk omega by k. This again looks like it is going to cause a problem, but we will see whether it causes a problem or not, right? So we look at the so-called p omega term. Okay, let's call this p omega. This part, I'll write it there below. Here this is production rate of omega term, right? And this is the dissipation rate of omega. You can call it epsilon omega or something. I'm only writing this. This terminology doesn't exist. Epsilon omega and all this. It looks a little funny, but that's okay. So let's look at the production term, p omega, which is c omega 1 pk omega by k. So y goes to 0, k should go to 0. It looks like it is going to blow up if you implement it like this. So let's see, we'll substitute what is pk. So I get c omega 1. What is pk? Pk is nothing but your 2 nu t Sij bar minus 2/3 k delta ij, right? And then I have the the strain rate part, dou I bar by dou xj followed by omega by k. So again eddy viscosity is k by omega, right? So I can replace the eddy viscosity here by k by omega. So if I do this, you can see goes away here, and also of course the two terms. Okay, let me just undo this. Okay, so let's expand this and see c omega 1 2 k by omega Sij bar dou I bar by dou xj omega by k minus c omega 1 2/3 k delta ij dou I bar by dou xj omega by k. Now both k and omega are cancelling it out. This has a profound influence in the k omega model. So if you recall the same p epsilon term, the production rate of epsilon in the k epsilon model, after dividing all this, the k is still remaining there in that equation. If we just go back, going 2 steps back here, so you can see it here in this part here. This particular term is now c epsilon 1 2 c mu k delta k Sij bar dou I bar by dou xj. So this k is there. So this p epsilon is still a function of k, right? So it is coupled. You need to compute k so that k value is used in the p epsilon value. It's a coupled system. Luckily, here the k dependency is gone. Your p omega is decoupled from k. So if you are numerically solving equations where any term is decoupled, it is great while solving it. This will not cause numerical issues, right? If let's say the k is actually giving bad values, your p epsilon will also give bad values because it's a function of k. But p omega is not a function of k, so this will also not pull it down. Okay, so this is one great advantage of a k omega model over k epsilon. Okay, so no k dependency here, completely decoupled. And here of course the k goes away, only omega comes in the p omega. So here no k dependency at all, right? So this is equal to c omega 1 2 Sij bar dou I bar by dou xj. So the p omega is depending entirely on the flow terms, just the strain rates here, not on the turbulence kinetic energy. So it is decoupled. Whether it has a consequence, because now the production rate of omega is a turbulent quantity, it's an inverse time scale, but it is now being computed using what is this, Sij bar and dou I bar by dou xj, right? This is also time scales only, but a flow time scale, right? So it is decoupled, numerically stable. Whether it is giving accuracy, that is another issue. Okay, so you can at least say now this term is now decoupled. So we'll see the other one, which is minus c omega 1 2/3 delta ij dou ui bar by dou xj omega. Okay, so the equation is completely decoupled here from p omega is decoupled from k equation. So this is good for, this smiley is for numerical stability. Okay, numerically stable whenever you have a decoupled system. Okay, that is fine. So entire equation also doesn't have any issues of divide by 0. So this is numerically stable, decoupled. That is also good. Two advantages here. Now we look into the other term, which is what we call an epsilon omega, which is C omega 2 omega square. So there is no problem here. Y goes to 0, k goes to 0. K itself is not appearing here. Unlike in the epsilon model, it's epsilon square by k. K itself is not appearing here, right? Again, no k dependence, or you can say decoupled from k. So in a k epsilon model, there is a strong coupling between the k and the epsilon equation. Okay, you need to iteratively solve this. But in the omega equation, both the production rate of omega and the dissipation or destruction rate of omega is decoupled from k, which is good for numerical stability. Okay, unlike the k epsilon. But this does not mean that standard k epsilon or any k epsilon models are unstable. So there are ways to handle that. This is just a modeling argument of having a new model, and